So let's see for ourselves. So this is another scenario where this is something we've been working on a long time. And it's a really common thread. It's usually the first thing that people think of when they decide, hey, I want to go use a quantum computer. It's route optimization. And for us, route optimization is interesting because it is very well researched. It's very well understood, and there's a lot of people who have opinions about this. So we started looking at route optimization back in 2018, and then again at the time we were using an IBM machine. And we could do 3 trucks and about 9 locations on that device. And I think it was a 11 or 10 qubit device. And so it was basically, and we were giving it some aids, allowing it to simplify the search, but it was able to solve some very, very rudimentary routes. And you see here some a screenshot of it figuring out fuel and time estimates for a series of deliveries around the Bay Area. And in 2020, we took another crack at it using quantum annealing technology and some of the quantum-inspired technology. So if you're not familiar with quantum-inspired, that's classical computers or classical technology that is running formulas that were kind of designed to run on quantum computers, but we're running them on classical computers using some shortcuts in order to get maximum performance out of those algorithms that we can. And sometimes when you're doing a quantum project, you learn something new about a formulation and you're like, well, I can't run this at scale efficiently on my quantum computers yet, but I can tweak it to run on a classical computer, and it may be something that I can go deploy and use today. And so we were in that mindset when we were revisiting this problem. And you can see we got 13 locations, 27 routes, and 200 constraints. So these are, attributes that would limit what selection is picked, which is common within solving these traveling salesman type problems. And you know that this is a classical NP-hard problem in computer science. It is truly difficult to solve. You can't really solve it exactly in many cases. What we've done is developed algorithms that allow us to circumvent and weed out and chop out scenarios, but really we're making assumptions and shortcuts in order to solve the problem today. We're not looking at all solutions or considering all possibilities. And so it is, a very important thing that we know quantum computers in the future will be able to solve with more precision at a larger scale. Okay, so a couple things here is also is that because this problem is so well researched, if you go to talk to folks, they'll say that, or you go talk to supply chain optimization folks, they'll say, we already have this solved. We already have solutions for how to solve supply chain. They're implemented today. They're implemented at scale. But the way that they're doing it, and they know they're doing it this way, but they say this anyway, is that they chop the problem up into smaller pieces and then solve smaller subsets of the problem, and then combine those smaller subsets to say what the solution is. But no one knows if that is a globally optimal solution. It really just solves for certain small areas and then combines the answers, and you hope to get something that is as efficient as possible. But it's not actually solving the entire supply chain problem for any one business, from manufacturing all the way to delivery to a shelf.